mean squared error. That's the equation for it right there. It's our good friends. Now, the thing about the mean squared error is some of your intuitions about what it does could be completely wrong. It's very sensitive to large deviations, to single large deviations in the data set. So here's a simple example. Suppose I'm predicting prices for 100 books, and I have two systems. One system predicts 99 prices exactly, so there's no error, the error is 0, and it gets one book wrong by $10. Okay? I have another system, and that system predicts every price wrong by a single dollar. Okay? Two very, very different performances, but the mean squared error is the same. Okay? Now you're looking at this and you're saying, okay, this is 10, this is 100, what's going on? The problem is the squaring. That one book, which is off by $10, turns into 100. That has the same impact as 100 books being off by 1. So a single incorrect prediction that is far off from the truth is going to have the same effect as lots of small errors. And that's something that you want to think about, whether that's what you want in your metric or not. Now, one reason why it's a bad metric is it will have a very dramatic effect on the kinds of models that you will learn in regression if you introduce outliers into the data. So look at this example. I've got one attribute x. I'm predicting y. The blue points are the truth, and the blue parabola is maybe what my regression system is predicting. Okay? And that looks like a reasonable fit to the data. Now, what happens if I introduce one outlier right there? What that outlier will do is now my system will try to fit that outlier. And the problem is, if you look at the difference between the true value and the predicted value, it's humongous compared to everything else. So what my system will do is it'll try to minimize that, the regression system. And what it'll produce is it'll produce a fit that looks like that. Right? That is actually a better fit to the data because of that one outlier. So you've completely changed the pattern just by introducing one outlier, and that will happen when you use mean squared error as a metric. Another property of mean squared error, it's very sensitive to the mean and the scale of the prediction. So if you get the mean correctly, that takes you a really long way. So for example, in this case, I could have, so the blue system is pretty good, but the orange system, so it gets the tendency right, but the mean is off, right? All the predictions are a lot lower, but it still captures the pattern, right? The green system gets the mean right, but it gets the pattern totally wrong. So the green system is actually going to have a smaller mean squared error than the orange system. So when you're doing regression and you're evaluating using mean squared error, getting the mean right is extremely important. And that's one reason why WECA actually uses a very strange metric instead of MSE. They use relative squared error. And what relative squared error is, it's just the mean squared error divided by what would happen if you used just the mean as a predictor. So instead of f of x, which is your prediction, you just take the mean of the values and see how far they deviate. So it's a ratio. If you get a number that's bigger than 1, this means that your system is actually worse than just taking the mean. And that